presentation today with comparatively short notice. Can you please present yourself first and then start the presentation?
Of course. Thank you so much for the invitation. My name is written on the screen, and as a background, I'm a geophysicist. I started my PhD in statistical volcanology, and then slowly moved to earthquake swarms at volcanoes, then in tectonic environment. And the last couple of years, I ended up also looking at the induced seismicity. I'm currently sitting as a researcher at INGV Bologna, so next couple of offices apart from Alex. And today I'm gonna be talking about this provocative title which is not provocative at all, but it's a part of what I found interesting in using seismicity to analyze injection experiments and try to understand what are the source processes leading to this seismicity. And even in these controlling experiments, I ended up saying that seismicity alone is not sufficient. So I just answered directly to the question in the title. But I will try to walk through all these bits and pieces that we put together to try to analyze the seismicity at Forge, and I will describe everything. And this work, it's in collaboration with people at ETH, and it's going to be part of a publication is led by Federica Lanzo. Then at some point it will come out, will be submitted to a journal, and so hopefully it's going to be out in the next month. So this is my contribution, which is basically focused on the analysis of the seismicity. I will start with a general introduction on what are the physical processes that one can expect where you do injection experiments. And particularly, I will focus on geothermal systems where injection is done to enhance the fluids flow circulation at depth. And in this slide, I will just walk through the main physical processes, as I said, that can generate seismicity. The first and the most known one is overpressurizing the system, increasing the pore pressure on faults that in turn diminishes the effective normal stress and causes failure, and so seismicity on faults that are already there. Then there is a pore-elastic response of the medium, so inject mass, and the pore-elastic matrix can also load this fault and trigger, lately in the last couple of decades has been proposed that also fluid-induced aseismic slip on faults, so with a process that is not exactly fully clear, but there are a lot of research going on. I'm not gonna focus in this presentation on pore-elastic loading, and there is a fourth, let's say, mechanisms that usually it's a bit overlooked, at least in what I saw in induced seismicity, which is hydrofracturing. So opening of fluid-filled cracks that in turn can generate seismicity. I want to stress, I will go through each one a bit more in details because these three models, they have a fundamental different way to trigger earthquakes. So seismicity failure on faults. So the hyper pressure increase is generally related to injection in a volume. You locally increase the pressure, you generate a pressure field that it's propagating in the medium, and it's increasing locally while propagating, it's increasing the pore pressure. If you are on a fault, this increasing pore pressure will diminishing the effective normal stress, so yielding a fault which is critically stressed to slip. And in this case, you need a fault there, you need pore pressure and an increase driven by the injection, the pressurized fluid that are injected in the medium. And if you look at this according to the Coulomb failure criterion, you will see that in this formula, you will increase the P, the pore pressure, the effective normal stress is gonna get smaller, and given a friction, you can let the fault slip. And you also can see from the More-Coulomb circle, basically you are moving this circle close to the failure envelope and let the fault slip. So the other process that I'm gonna be focusing, it's a seismic slip. This is a very famous paper by Yves Guglielmi that in 2015, they injected fluid on a fault in this laboratory in southern France. And they measure all the seismicity through geophones and other sensor, but also they installed this three-dimensional strain meter, is called the SimFIP, right at the bottom of the fault, where also they did the injection. And if you see this complicated plot where the top two lines are the pore fluid pressure increase and the injection rate, and you focus on what this strain meter, the deformation of the strain meter, the displacement that has been measured on the fault in this point here, you see that there is an increase of the opening and of the shearing of the fault, the black lines, that it's anticipating the start of the seismicity that you can see from this orange line here. So the fault starts to move aseismically before or some seconds, some hours before, some minutes before the start of actually the seismic activity. So this process has been then investigated in many other cases and with other instruments. It's very difficult to install instrument to measure the formation, but it seems also a plausible or viable mechanism to induce seismicity. And a simple model that can explain this one was put forward by Fred Kappa and co-authors in this paper in 2019. Basically, the model is very simple. You have the injection point here. You inject fluids on a fault, which is either velocity weakening. So basically, you have asperities that can fail. And as you can see, as long as the fluid is injected and the pressure, the fault gets unclamped, so dilate. And you can see from the other two plots where you have the fluid pressure and the stress, and each line, it's a snapshot in time of the evolution of this aseismic crack here, because basically you induce unclamping the fault and a seismic crack to propagate. And what is interesting is that at the edges of this fracture, you have an increase of the shear stress. And this increase of the shear stress triggers seismicity that are depicted here as earthquakes on this point. So this is a very simple model. You have the expansion of the aseismic slip induced by fault unclamping by the fluid pressurization, and this in turn can trigger seismicity on the expansion edges of this crack. And then the third process is hydraulic fracturing. Usually it's done on industrial operation to enhance, for example, permeability and induce fluid circulation, but also to do borehole measurements in terms of stress, this breakout that they do. But physically speaking, what happens is that you increase you inject fluid, pressurized fluid, they open a crack which is filled by fluid in the host rock, which is depicted by this 2D experiment. And this crack, as long as you are pumping, so you are keeping the overpressure high, can expand, and the seismicity is triggered around this crack, because the crack is aseismic by itself, because it's filled by fluid that cannot have shearing, but the seismicity is triggered on optimally oriented faults, which are around this expansion of this fluid-filled crack. And in order to explain the stress that you can have when you have a fluid-filled crack, I go back to my background, which is still as a volcanologist, and we published in 2015 a paper on a giant dike intrusion in Japan, away from the Miyakejima Island. And in the top view, you have this elliptical crack, which is filled by magma in this case. And in the other two panels, you have the Coulomb stress that is induced by the opening and the expansion of this elliptical crack. And if you focus at the point A, so this is horizontal crack, is expanding along the y-axis, opening against the x-axis, which goes into the screen, and then the depth is the z-axis. So at the point at the point A, you have this dike, which is this white bar here, and the crack will put compression, so stress shadow, negative Coulomb, orthogonal to the dike plane, but it will increase strike slip faulting ahead of his tip. So in this region, you would expect strike slip faulting. While if you look at the point A, so a map view looking from top, and you have the dike you are seeing from the back, and the dike is again this white bar, you would expect normal faulting on top of the dike in this B region. And this is well known in volcanology. You have the graben faulting occurring on top of a dike. And then in the C point, you would expect focal mechanisms that are a oblique mechanism, so they have a part of normal faulting and strike slip. So that's the stress that is induced, and if there are optimally oriented fault, those can fail because of the stress induced by the tensile crack. So this process is fundamentally different from the one that we saw before, where you expect to have shearing on a fault or stimulating a fault inducing a seismic slip. And that was testified also by the focal mechanisms that we recorded. They were predominantly normal faulting and strike slip with oblique mechanism. And this is the dike, which started from the Makojima Island here, propagated for 30 kilometers, and then started to expand. And I want also to notice these two wings lobes that are dominated by strike slip that are ahead of the tip of this propagating dike and then inflating dike. So this is the seismicity just expected by tensile crack, upscaling to a very large dimension. We're going to downscale it in our case of induced seismicity on a decameter scale. But just to say, what I want to stress so far is that these three processes, they have three different physical mechanisms to induce earthquakes. And the test bed that we used to analyze, so that we had analyzed in terms of physical processes in the project that I used to work, it's FORGE, it's the Frontier Observatory for Research in Geothermal Energy. It's in Utah, in the desert of Utah. It's a huge field-scale laboratory where they are testing the feasibility of the Enhanced Geothermal System. It's in the desert because the population will not affect in case of induced seismicity. And this is the view from top of the facility. So you have the 16B, which is the production well. At that time, they had only one. Now they drilled another one which is the circulation and for the recovery of the heat, the thermal water, and the dashed line is the strike of this well. And then you have three monitoring wells, which were equipped during the injection by geophone chains. And if you see the footprint of FORGE, is this one. This is the injection well, and the seismicity that was stimulated or induced during the 2022 injection in 3 stages. It was April, and there were stages a week apart, lasting for a couple of hours. And in 3D, you can see that the stimulation occurred at the toe of the 16A32 well, which is here. And sorry. And in 3 different intervals. And that has been recorded by the 3 boreholes, so 3 with geophone chains, and also they had a borehole equipped with DAS. Unfortunately, so that's exactly the sketch where the injection were done. S1 was stage 1, S2 was the second stage, and the third stage S3. The first one was really at the toe of the well in an open hole system. The other for the other two stimulations, they did a perforation test. So they injected before in a perforation hole that was created by an explosion before the injection. Stage 1 and stage 2 had a bad coverage of the geophones because basically they cooked due to the high temperature at almost 2,500 meters depth. And so what we are going to present you is just the results of the stage 3, where nearly 20,000 events were detected, and 5,000 of those, they had a very good hypocentral solution with magnitude estimation, and they were all manually revised by Geoenergy Swiss. And so it's a very wonderful catalog, and in this case, it's going to be stage 3. But before to go to the seismicity, I will talk a little bit about the stress and the local stress, the in situ stress that you have in Forge. Because being a laboratory, when they drilled the well, they basically also did all the sorts of stress measurements and breakout and logging of the wells. On the top, you see the orientation of the tensile fracture measured at the Forge, and they are basically oriented 20 degrees north to east, and it is pretty coherent for the three type of measurements in the three type of different wells. And they also measure the stress gradient, and from the stress gradient with depth, you can retrieve the absolute stresses that are in place with the orientation. So I'm reporting here the vertical stress, sigma V, or in this case, sigma 1, then the maximum horizontal and the minimum horizontal, and the numbers below are the range of variability that they have in terms of these measurements. And I wanted to stress that it's on a regional scale, it's a normal faulting system, but locally you can have a normal stress where sigma 1 is greater than sigma 2 and sigma 3, but also due to the variability of sigma H max, that could be also that you have a flip of the stress field. From normal faulting, it became a strike slip regime. And in this case, it's essential also in the analysis that I'm going to present to have this in mind. And in order, when you have this stress field, you can also expect what is the slip tendency. So which are the faults that are expected there and their orientation, which is also going to be useful for the analysis that we performed. So if you have a tensile crack opening in this stress field, either it's a strike slip or normal faulting, the plane of the tensile crack is going to be parallel to the plane formed by sigma V and sigma H max, as I depicted here in this simple sketch of a tensile crack. The strike is going to be in this direction and is going to open always against sigma H min, because a tensile crack opens minimizing the energy, so against the minimum compressive stress in the field. They are very wonderful, the stress meters. But this is for a tensile crack opening in this field. The geometry is important also for later on. But what about normal faulting? For normal faulting, according to the Andersonian theory of the fault, you have that the strike of the normal faulting is going to be parallel to sigma H max, if the stress field is a normal faulting one. And for a friction of 0.6, they will have a dip of 60 degrees, so classical Andersonian theory. But the strike is going to be, I stressed, along the sigma H max of this normal faulting. And then what about if it's a strike slip fault, so in a strike slip regime? For this case, if you consider a friction, classical friction of 0.6, the strike of this strike slip fault would be north-south oriented, and the dip, of course, is going to be vertical. So this is the geometry or the type of faulting that we expect, or the geometry expected for a tensile crack. And now we go directly to how the seismicity looks like. I will show you a video to see and appreciate the 3D development of the seismicity on the left, but I will start before a little bit showing that the magnitude time plot, you see that there was some hydraulic operation, the injection operation, and the seismicity went on during the shut-in phase and also faded out during the flow back, because in each stage, they removed all the fluids from the system that they had injected. In the video on the left, you have the stress field, as I depicted before. The point, the triangle, is the place where they injected. And in this case, we know because they did this perforation shot before the injection, and the perforation shot was located by the seismic network. And all the seismicity is also located relative to the perforation shot. So in this case, we have a favorable condition to know also, or roughly know, I mean, with a good approximation, where the injection was in the interval, which is the black line, the well. And you will see the seismicity expanding. The red dots are the expansion in time, which is depicted up. And then in gray is the background seismicity. And count that the injection lasted 2 hours, as you can see. So at the 15:40, it's almost over the injection, but the seismicity will propagate. So I'll start the video, let you enjoy. You can see that the size of the events is the magnitude. I forgot to say, and so you have a early magnitude on the left side, but then the seismicity starts to propagate outward, and the largest magnitude occur on top of the seismicity cloud. You see that there are some cluster zones, there is a central cloud, and there are some others, wing lobe, as I showed you before, that are part of the seismicity, and they are branching off the main seismicity cloud that is here in map view. Okay, I go for the time evolution of the seismicity and the hydraulic parameters. You see in magenta is the pressure measured at the interval, and in blue is the flow rate, which is liter per minute. So they really pumped a lot, like 90 liter per second or something like that, at maximum 100 liter per second in a usually stepwise way in the 2 hours. Then they start to decrease the flow rate going to 0. And you see that the pressure immediately goes up to 50 megapascal, which is in the range of the sigma 3. So the minimum horizontal stress. And the seismicity didn't start right away when the injection started, but he had a few minutes, a bit, 15 minutes or something like that lag, and then gradually increased, as you can see from the bar of the histogram, that are earthquake in 6 hours, in, I don't know, a quarter of hour. And you see that while the hydraulic operation were going down, the seismicity stayed at a higher peak and then slowly faded out. And faded out, as you can see also from the propagation in the northern direction and time of the seismicity during the flowback phase, but the higher seismicity stayed after the hydraulic operation were over, and the largest magnitude events that occurred on top of the seismic cloud occurred during the shut-in phase. This is typical of this experiment. I learned that is typical. But it's what is very interesting, but you also seen from the video that you have a sort of bilateral propagation of the seismicity. It's increasing sidewise, and you have also some branching off of the seismicity which have host larger magnitude events. The largest magnitude recorded was at 0.5 in this case. Here the injection stopped, but you see that the propagation still going on. The first analysis that we did in terms of was Gutenberg-Richter, and it was just to have an observation to see whether the Gutenberg-Richter model can explain some of the feature of the seismicity, and we did it an estimation of the Gutenberg-Richter in time and in space, grouping together 300 neighboring events. So for each point, there is a B value referring to the nearest neighbor's 300 events. So it's a smooth pictures of the evolution of the B-value. I wouldn't like to comment too much on that in terms of the physics, because you have a clear departure from the frequency magnitude distribution from the Gutenberg-Richter model. But what is very interesting is the B-value is, sorry about that, is telling us that the largest magnitude events, so the lowest B-value, it's at the edge of this propagating front of seismicity. While inside, sorry about that, while inside the cloud, the B-value is higher, so there are much smaller events compared to the propagating front of the seismicity. So what I did in order to fit the previous model I presented, physical model I presented, is I took the fundamental equation or the very simple equation for each of the model and tried to fit to the data. And for the pore pressure, I don't need to dwell a lot on that, but we used the classical diffusivity model for the pore pressure, which was used in reservoir induced seismicity back in the 80s, and then used also by Shapiro and co-authors a lot to explain. And what I wanted to stress that the equations are very simple. They are equations that are built to be fit to the propagating front of the seismicity, and in terms of this distance time plot. So the distance, which is RF in this case of the front, is time dependent and is proportional to this seismic diffusivity times the time, and it's a parabolic relationship. So having the front, the propagation front, you can fit this model, get the parameter, and see if they are physically plausible. Later on, they also introduced an equation for the back front, so I'm going to use both of them to try to fit to my data. But then for a seismic slip-induced seismicity, there are not so many models around, but in this case, Philippe Darren co-authors, they just came up with this simple complicated model in terms of the mechanics included, but in 2 words, is basically simulating an aseismic rupture on a fault, which has also some points, some asperities that they can fail seismically. So the crack, the shear crack is propagating aseismically, and while it encounters this asperity, let them fail, and so produce the seismic response to an aseismic crack. What is really interesting, without to go too much into details on this model, is that at the end, it gives out as an output this simple equation, which links the propagating front of the seismicity, which is failed according to the expansion of this crack, with the injection volume in time, through a constant which is a function of the fault parameter stress drop, fluid compressibility. And this, it's a parabolic equation that in a distance volume plot you can fit to the data and see whether this model is fitting the expansion of the seismicity. So very simple, and also links the 2 variables that we have control in, because the volume injected and the distance of the expanding seismicity front, it's known and can be measured. I mean, one it's part of the experiment, the other one can be measured empirically. And the other, we also introduced for a tensile crack model, a very simple penny-shaped crack model. And a penny-shaped crack, it's analytical expression for a tensile opening of a crack, a circular crack. And in this case, I'm depicting that you can inject inside, you can open this tensile crack and then let it expand, either in side view and in map view here. And for this crack, we have analytically the volume of the crack, which is proportional to a radius, which is this A cubed, through some elastic constant and the P is the overpressure. So knowing the volume, you can make few simple assumptions, which is, one is that the seismicity is occurring at the expanding edges, leading edges of this penny-shaped crack. And so the propagation of the seismicity, so this RT front, is proxy from the expansion of the crack's radius. And if you assume that there is no leak off, so the volume of the crack is filled by the injected volume, so there is no leakage of the fluid, which in first approximation, the first instance is a good approximation. Then you can use the propagating front as the radius of as a proxy of the radius of the crack. If you have this assumption, then you can retrieve a simple equation, which is a cubic law between the volume injected and the expansion of the seismicity front through a constant which is proportional to the elastic parameters of the medium and the overpressure. So we have three equations, and these three equations can be fit directly to the data, as I did it here. Two disclaimer before, since diffusivity, the model, it's dependent through time, and the other two from injection volume, I just fit the data up to the point where the volume was injected. So the first 2 hours and a half of the injection. And for the two models, depending on the volume, I use the time volume transfer function to have everything on the same plot. And in this case, I fit the data of the distance time plot against the propagation front, which is depicted by the 99th percentile of the distance traveled by the seismicity front. So basically the gray squares. I will start with the diffusivity model, which is the only one that can propagate after the volume, the flow rate, it's 0, because the pore pressure, the pressure diffusion can go on almost forever. And for this case, we fit the model. We had a good value for the diffusion of the front, which is a reasonable small diffusivity constant value. And the adjusted R squares for this fit is pretty much 1, 0.95. We have problem to fit the back front of this model because the adjusted R square is very small, and also we got a different diffusivity model, even smaller than the one before. When instead you use an aseismic shear crack, in this case the black line here, and you fit this volume and time, you get a constant which has a plausible value, and in this case, the adjusted R square, it's again 0.9, so a very good fit. Then when you put in the tensile crack, again, the model fit the data very well, and you have an even, or maybe the highest adjusted R square, which is 0.97. So in this case, when I started to play with this data, I was hoping that one of the model would stem out against the other, but it's not actually the case. So that's the title, basically. In my opinion, and with whatever goodness of fit statistics you want to use, you are not really able to distinguish which is the best model just based on the RT plot, so this distance time plot. So in order to go a bit deeper and try to understand which was the most favorable model without having the deformation in this case that would have been solved all the problem, I will make each of the model in context of the stress field before. So basically, we asked ourselves whether the geometrical distribution of the seismic cloud would have fit one of the three different models in terms of the stress and also the geometry, as I said. So I just remember you the geometry of the stress tensor at Forge. And in this case, what we did, we simply fit a geometrical surface on the fault. We used principal component analysis, and we found out that a plane can easily fit, or it's a good fit for the seismicity cloud, because the variance orthogonal to the plane, I guess I cannot see, but it's only 3% of, so giving up for one dimension, we're going to lose only 3% of the variance into the data. And in this case, the geometry of the plane, it's with a strike which is 15 degrees north to east, and a dip which is subvertical, basically 80 degrees. So basically, as you can see from the map view, the plane is sub-parallel, almost parallel to sigma h max, and it's nearly orthogonal to sigma h mean. And it's almost vertical. And if you rotate, this can be better seen when you rotate the plot, in the direction of the plane, you see that the sigma h max is parallel to the plane. So basically, if we had, as I said before, a tensile crack inducing seismicity on optimally oriented fault while expanding at the leading edges, you have that the plane it's telling, and the plane it's somehow a proxy for this tensile crack. The geometry of the crack is what you would expect. So the crack's plane, it's on the plane sigma v at sigma h max, and it's opening against sigma 3, and the seismicity would be caused by the expansion. So in terms of the geometry, a tensile crack would sit there, and the geometry and also these wing cracks, lobes that you have, can be all explainable by the seismicity induced by a tensile crack. While we worked a little bit on the Coulomb more circle for the normal faulting and the strike slip, because also we have to take into account that the seismicity occurred on already existing fault. So basically, we calculate the Coulomb, more Coulomb circle for an intact rock given the stress field, which is the orange. According to this equation, we had a very high friction coefficient. And if we include the pore pressure, which is in this case a lower estimate, is 40 MPa, while they get to 50 MPa, you would shift this more circle close to the failure. But at the same time, you will end up with a zero effective normal stress. So this analysis, that's done for a strike slip fault. And this analysis will tell us that basically effective normal stress is zero, you are opening. So you get to the failure, but in a way that maybe you are opening something. And it's exactly the same from the normal fault. So that's the intact, very far from the failure envelope. So in this geometry is not optimal oriented for the stress field, but then you increase the pore pressure through the injection, and then you get again to touch the failure, but again at zero normal stress condition. So for this analysis, we have a reasonable high static friction coefficient that you derive from this case, and you get zero effective normal stress condition. So it's unlikely that they are shearing on a fault, but it's more than maybe it's a tensile crack. And I will go to the conclusion immediately, saying that the distance, time, volume plots or way of fitting the models, in this case, are not conclusive to discriminate which is the physical process triggering seismicity. The seismicity is indeed compatible by an hydrofracture, so a tensile crack which is opening and in turn it's inducing seismicity. But even in this case, we cannot completely rule out that it's also shearing along pre-existing fault, either with a seismic and seismic slip involved. So in this case, my advice in general is that when they do this experiment, they should also put some deformation measurement data, and they are doing it, because only the deformation would have been able to tell us whether we had an opening, we had an extra slip on a fault, and then in that case, you can do a full analysis on the physical mechanism. In this case, we did our best. We have a tendency to say that hydrofracture is what it caused the seismicity, but again, we cannot really completely rule out the other two cases. So for this one, I finish. I thank you for the attention, and I'm happy to get questions from you.
Thank you very much, Luigi.